Okay, so these are going to be the notes for chapter 22. We're going to start off with a little history lesson. So when we deal with inference on means, there's something different about it compared to proportions. And the man who found this, his name is William Gossett. And let's see. He worked for Guinness Brewery in Dublin, Ireland, and his job was to make sure that the stout was of high enough quality before it was sent out. And so while he was doing this, he was using traditional statistics, looking at proportions in the normal model. And when he was doing this, he realized that his process wasn't making the type 1 errors 5% of the time like he had predicted, but it was actually 15% of the time. And so he was upset about this or baffled by this because he couldn't figure out what was going on. And so he ended up taking time off of work and went back to school to study statistics. And when he was doing that, he determined what was wrong, and he learned that for means, you have to do something called a degrees of freedom. And what's interesting about this little side note is that he wanted to publish the paper, but Guinness didn't want him to publish the paper because they were worried he was going to publish all their secrets on how they made their beer. And so he had to publish the paper under student X or student. And so now when we talk about a mean model, it's actually called the student's T model. And it was never named after him. Okay. And so if you look here, the blue right there is what a normal curve looks like. And here's the mean. And if you go 3 standard deviations out to the left or 3 standard deviations out to the right, that's where it about ends. And that's what a normal model does. But what he was finding with the mean is with 1 degree of freedom, it was a fatter tail and it didn't go as high. Okay. So then let's look and see what happens with 2 degrees of freedom. Again, the blue is the normal. The green is what 1 degree of freedom is, and then the red is what 2 degrees of freedom are. Okay, so if you notice, I'm a little closer to the normal model now with 2 degrees. And then the same thing's happening here with 3 degrees. I'm getting closer and closer to the normal model, so that's 3 degrees of freedom. There's 5. There's 10, it's getting closer and closer. And finally, 30, when you get to about 30 or higher, you're pretty much at a normal model. Okay, so when we think about inference, when you're doing a student's T model, because that's what means are, they're students' T's, it depends on the family. It's a family of distribution that depend on the degrees of freedom. And degrees of freedom is the abbreviation for it is DF. And the way you find it for means is just n minus 1. And remember, n is your sample size. All right, so there's some things that we want to remember about means. Or not about means, but around the student's T. And remember, the first one is the smaller the sample is the fatter or the thicker the tail is. So if you remember in our video, let's say this black one is a normal model. If I have a smaller sample size, it has a thicker tail right here. That's what I mean by that. The fatter it is or the thicker it is. It's kind of that height. And as you get a larger and larger sample size, it gets closer and closer to what a normal model will look like. All right, the next thing we need to know is as your degrees of freedom increase, 2 things happen. The first one is your center and shape stay the same. So if it was unimodal, it stays unimodal. If the mean was at 25, the mean stays at 25. What happens though is that the spread becomes smaller. Everything gets closer and closer together. So, ooh, that's horrible looking smaller. So even though the shape looks like it's a little different, it's still unimodal, so it stays the same, but what's happening is it's getting closer together, and so that's why the spread gets smaller. This last one kind of is common sense, but we might want to just have it there. Some of you like to have some stuff written down just in case. Remember, if you increase the degrees of freedom, it's the exact same thing as increasing the sample size. And the reason that is because you find degrees of freedom by just doing the sample size minus 1. Okay, so when we work with inference about means, and that includes confidence intervals and hypothesis testing, we still have our conditions. One thing that's nice is that you already kind of know these conditions, okay? You know the randomization condition. It has to be a random sample. You know the 10% condition. This is still less than 10% of population. And you know the independent. Now, this is just saying that the means have to be independent of each other's. Okay, the nearly normal condition, this is the one that's a little new. And nearly normal just means it needs to be unimodal and roughly symmetric. How roughly symmetric? Well, that depends on the sample size. So let's look down here. So depending on what kind of sample we have and what size it is, we have to look at these different sizes, what is required. When you want to check to see if something's nearly normal, you're actually going to have to look at histogram. So sometimes they're going to give you a picture. Sometimes after you put the numbers in the calculator, you have to actually go to the graph and look at the histogram. Okay, for a small sample size, now when we say these numbers are not exact. These are about 15. So if it was 16, I'd count it. If it was 14, I'd count it. I know it's a little annoying that it's not a cutoff number, but there really isn't any cutoff numbers in stats. Okay, so if you have a small sample size, then this needs to, the histogram needs to look pretty close to normal. With no outliers or skewness. If you have a small sample and outliers, or a small sample and it's skewed to the right, then you cannot use the student's T model. Okay. For a medium sample, and again, these numbers are kind of estimates, it's about between 15 and 40, about those numbers. If you have a small sample, a medium sample, the T model will work well if unimodal. Oops. And symmetric. So if skewed, do not do it. No. Okay. Now here's the thing. If you have outliers, depending on how far they are, you have to look at it carefully and kind of see whether or not you will do it or not. If the outliers are equal on both sides, then it should be okay. But if you have an outliers just on the right side, then that's skewed, so you wouldn't want to do it. Okay? Kind of depends more on skewness. Okay, so now when we get to a large sample, and a large sample is about 40 or more, it will work all the time. It will safe to work even if skewed. safe to use, oops, even if skewed. Okay. Now, the only thing here is if you have outliers on this data, you're going to run it twice. You're going to run it twice. You're going to do it once with outliers, and then you also would do it without the outliers. Sometimes the outliers are what actually tells us this story about the data. So sometimes you have to look at it both times. All right, so if you have a small sample, it needs to be normal. If you have a medium sample, it needs to be unimodal and symmetric. Okay, if you have a large sample, it can be almost anything and it'll work. So you have to be aware of those things, and that's the nearly normal condition. All right, what we have next is margin of error. Remember margin of error, we've done margin of error before. Let's highlight this. Oh no, hold on. Okay, so we've done margin of error before. Remember when we do a confidence interval? Remember this, our confidence interval? So if this is our confidence interval right here, this on this side is the margin of error, and on this side is a margin of error. So you have two margin of errors with your confidence interval. So when we did our confidence interval for proportions, our letter here was a Z because it was proportions, which is our Z. This is our critical T. So it's the critical point for T. And again, it's based on degrees of freedom, so that's why it's n minus 1. This is just our sample standard deviation. Okay. Now, you've done confidence intervals before. The only difference between what we're doing now and what we've done before is the fact that we have to use a critical T versus a critical Z. Okay. But you find them the same way. The big difference, though, is that you are going to use the inverse T function. And unfortunately, I don't have a calculator connected to my computer right now, so you're going to have to kind of listen to the steps. So the way you get the inverse T, let's write these steps. You're going to hit second, and then the vars button. And then you're going to choose number 4, which is inverse T. Oops, and that's lowercase I. It's the same place where you find inverse norm, normal CDF, all of those things. So we're going to do inverse T. The first thing is the area to the left. Remember, it needs to be a decimal. 90% is 0.9. Right? 5% is 0.05. So remember, you have to write it as a percent, as a decimal. And then the next number is your degrees of freedom. And the way you do that is just n minus 1. Okay? So remember here, let's just kind of do a quick review. Remember, if I want a 92% confidence interval, that means 92% is on the inside. So over here is 4%, and over here is 4%. And so I would do my inverse T of 0.04 with whatever n minus 1 is. Okay. All right, so what we're going to do now is we're actually going to practice some of these problems. And so we actually have this one set up right here because it's 92%. So we're going to do the inverse T of 0.04. And right here, it tells me my degrees of freedom is 20. So since it tells me my degrees of freedom is 20, I'm going to plug that in. And you should get negative 1.84. Now, remember with critical T's, sometimes you're going to get negatives. I'm okay with you keeping it a negative. or making it a positive 1.84. We should actually, though, put the 20, though, because it's the critical T for 20. Okay. All right. Let's try this next one. If I have 96% in the middle, then I have 2% over here and 2% over here. So it'll be 0.02. And again, this is my degrees of freedom. So it'll be 31. And so inverse T of 0.02 with 31. And so my critical T for 31 is negative 2.14, or my critical T for 31 is 2.14. Again, I'll accept either. Okay, so now for this one, we need to calculate a p-value when T is greater than 1.45 with 8 degrees of freedom. Okay, so what this is saying, a t-value, that's just saying a t-score, which is how many tick marks you are away from the mean. So here's my mean, and I go 1, 2, 3, 1, 2, 3. This is 1.45. So I'm going to shade here because it's 1.45 above. Okay, what we have to do here is we are finding the percent of time that it's in the shaded area. Usually we would do normal CDF, but this is not a normal model. This is a student's T model. And so we need to go to our steps. It's second vars again. So second, and then vars. And to find the area shaded above, we're going to choose number 6, which is TCDF. And again, I apologize that I don't have a calculator to show you. I'm hoping to get one installed on my computer this week. And so it's going to ask you the lower. And so the lower for this one is 1.45. It's going to ask you the upper. And the upper, I'd pick a big number, maybe 1,000. And then it's going to ask you the degrees of freedom. And our degrees of freedom is right here, is 8. And so when I do that, I get a 0.093. Okay? And so let me go back here. I'll show you. I can't show you on my screen, actually. Okay, so now we're going to do the same idea here. Let's change colors again. So, again, that's my t-score. So I'm at 0, and then I'm 1, 2, 3, and I'm negative 2.3 standard deviations away, which is over there somewhere. And so again, I'm going to do this right here. Second vars, number 6. My lower for this one now is a negative, maybe 1,000. That would be your lower. And then your upper is the negative 2.31. And then for this one, your degrees of freedom is 12. And so this is 0.0197 or 0.02. Because that 7 pushes that 9 up, which pushes that 1 up to a 2. Okay. All right, the last one I want to show you like this on this video, and then we'll do a separate video for the other examples. Oh, no, we're going to do the same video here. I have them there. I forgot I had them there. Crud. Hold on. There we go. Okay, so same idea. Okay, so 2.4 is here. And you see how it says to the left? Well, when you have an absolute value, remember you're also going to have the other side. Because remember, the absolute value, when you have an absolute value, there's a positive answer and a negative answer. So that's 2.4, 2.14. And the negative answer is 2.14. Well, long ago with your algebra years, you solved some of these problems. And the first problem, remember, it stayed exactly the same. But the second problem, when you made it negative, you also flipped your inequality because you made it negative. So that means it's to the right. So the shaded area here is what's in between. And so your lower would be negative 2.14, so go TCDF again. Your upper is this positive 2.14, and your degrees of freedom is 19. And so the percent between those two lines is 0.954. Okay, so instead of moving on to the hypothesis testing in this video, we're going to stop this video here, and we'll make a separate video for hypothesis testing, which is the next problem. And then we'll make a separate video for the next problem that talks about confidence interval.